Uh, yeah, sure, sure.
Okay,
Um,
great. Then, yeah, welcome everyone. And today we're very happy to have Agostina Jakovic from the University of Luxembourg. And he's going to be talking about categorical Torelli theorems for final threefolds, A sub B. Please go ahead.
okay, thanks, Pedro, for in inviting me to speak here. It's great to give a talk here, and thanks everyone for coming. So yeah, let me kind of give an overview of what I'll be speaking about today. So I'll give some background on the derived Torelli problem and derived categories, semi-orthogonal decompositions, and then the categorical Torelli problem in the setting of Fano threefolds. And then I'll look at kind of different approaches to proving these types of theorems. So we'll start with a kind of geometric example where the so-called Kuznetsov component um, is simple in some sense, equivalent to a derived category of a curve. Then we'll look at kind of moduli theoretic approaches, and then some more Hodge theoretic oriented approaches, of which there are a few. So hopefully we'll have time to look at all of them. Um, right, so the hopefully this yeah, let me just move this to the side. Yeah, so the kind of key question is how much does a category determine a variety, a category associated to the variety? So let X be smooth projective over the complex numbers. Then if we consider its derived category of coherent sheaves, the kind of derived Torelli question is how much does dBx know about X? Um, so if the canonical bundle of X is ample or anti-ample, so in particular if or in one of these cases, in the anti-ample case, if X is Fano, then an equivalence of the derived categories of X and X prime gives an isomorphism of X and X prime. Um, right. So in the Fano case, the derived category does determine X. Okay, but in the Fano case, the derived category decomposes. So first I have to tell you what I mean by a derived category, or really any triangulated category decomposing, but for this talk, that's kind of specialized to derived categories of varieties. And I mean, to illustrate the notion of an SOD, I'll kind of use the simplest case where we just have a kind of two-piece SOD. So if I can write dBx like this with AB in these angle brackets, then we say it's a semi-orthogonal decomposition if the following two conditions hold. So if well, actually, something I didn't write here, A and B have to be admissible subcategories of dBx. So in other words, their inclusions into dBx have both left and right adjoints. But right, so the first condition is that this A and B, they generate dBx in the sense that any object, if you give me any object in dBx, I can generate it from objects in A and B by taking some combination of cones, shifts, and direct sums between these objects in A and B. So that's the generation condition. And then the kind of orthogonality condition um, specifies that you can't have any Homs nor X's from right to left. So if I take an object in the subcategory B, and then an object in the subcategory A, and then if I take Hom or any X from the object in B to the object in A, that Hom or Ext will vanish. Okay, and the point is that so for Calabi-Yau threefolds, for example, the derived category is indecomposable in the sense that it has no non-trivial semi-orthogonal decompositions. But when we have a Fano variety, for example, we always have a non-trivial semi-orthogonal decomposition of dbx. So below here, I've written the simplest one that you can always take when x is a Fano. So the structure sheaf of the Fano is exceptional. In other words, it's kind of graded space of Homs is just a copy of C in degree 0. This means that we can take, well, as one of the subcategories, in this case, B, as just the exceptional object O, and then we can just take its orthogonal complement, and then these two, the complement and O, will give us a semi-orthogonal decomposition of the derived category. But sometimes we'll have a larger exceptional collection. So what I mean is sometimes we'll have more line bundles or vector bundles rather than just OX, and then the orthogonal will somehow be smaller. So I'll say more about this later. But somehow this is the kind of most simple SOD you can take for Fano varieties. And yeah, let me say now that for this talk, I'll kind of focus on smooth Fano threefolds of Picard rank 1. So there are 17 deformation families of these Fano threefolds. They've been classified. And in the Picard rank 1 case, the thing that classifies them into, well, I should say the things that classify them into deformation families are their index and then their degree. So index is just the integer such that kx equals minus I times the hyperplane class. And then the degree is just the hyperplane class cubed. Okay. Right, and if you remember in the first slide, I kind of gave the statement of, in particular for Fano's, derived Torelli holding. So the derived category of a Fano determines it up to isomorphism. Well, now that we've got this notion of semi-orthogonal decomposition, and since we know that Fano varieties always have semi-orthogonal decompositions, we can kind of ask, does something less than the whole of dbx determine x up to isomorphism? So can I take maybe one of the parts of this semi-orthogonal decomposition, and then will that determine x up to isomorphism? Okay, so let me start with an example. So this is this geometric example that I mentioned in the plan of the talk. And for each of these examples that I give in the talk, I'll kind of be focusing on one of the 17 deformation families of smooth Picard rank 1 Fano threefolds. So this is one of these deformation families. So this one's given by intersections of two quadrics, two four-dimensional quadrics, giving a threefold. So it can be shown that if we have an intersection of two four-dimensional quadrics, then X is Fano, its anti-canonical is ample, it's got Picard rank 1, index 2, so meaning that Kx is minus 2h, and degree 4. And also vice versa, it can be shown that if you, that if you take a variety with these properties, so smooth Picard rank 1, index 2, and degree 4, then you'll always get an intersection of two quadrics. Okay, so let's do some geometry. Let's take the pencil of quadrics generated by these two quadrics Q and Q prime. So parameterized by P1. Well, the generic element of this pencil is smooth, but there are 6 points where the Q lambda is singular. So let's call these 6 points lambda 1 up to lambda 6. These 6 points of P1. So smooth quadrics have two choices of ruling, but the singular ones only have one choice. And the thing parameterizing our pencil is P1. So this gives us a double cover of P1. So two sheets when we have two rulings, and one sheet when we have the singular quadrics. And that's the same as saying our double cover is branched or ramifies at these 6 points. Well, branches at these 6 points in P1, lambda 1 up to lambda 6. And a double cover of P1 branched in 6 points, that's a genus 2 curve. Right, so the above argument gives an isomorphism between the moduli space of genus 2 curves and the moduli space of the deformation family of this type of Fano threefold. So the moduli space of index 1, degree 4, smooth, Picard rank 1, Fano threefolds. Okay, now let's look at the derived category of these types of Fano threefolds. So not only can we take just the structure sheaf as the thing on the right-hand side of the decomposition, actually the structure sheaf and the structure sheaf twisted by the hyperplane class, so O1, these form an exceptional collection. So I mean, they're both exceptional objects, and there are no HOMs from OXH to OX by Kodaira vanishing in this case because the canonical is minus 2H. Right, so this gives us an exceptional collection, so we can put that as the right-hand side piece of our semi-orthogonal decomposition and then take the complement to it. It's just in this case I've actually defined the complement to be this QX, this Kuznetsov component. So yeah, as I said, this Kuznetsov component is the right orthogonal to this OX and OXH. And well, more explicitly, it's all of the objects F and dBx such that there aren't any HOMs or Xs from OX to those objects, nor from OXH to those objects. And it's called the Kuznetsov component because Kuznetsov did a lot of work on these non-trivial components of derived categories for many of the deformation classes of Fano threefolds and also higher dimensional Fano varieties. Okay, and here's why this example is geometric. So the Kuznetsov component in this case, it's equivalent to the derived category of a curve C, but not any curve. Actually, the curve from this isomorphism of moduli spaces. So when you take an X, you get an associated C. So this is exactly that curve. So therefore we get a categorical statement, a categorical Torelli statement immediately. So if we assume an equivalence of Kuznetsov components of such x and x primes. So x is the intersection of two quadrics and x prime is another intersection of two quadrics. Well then, because the Kuznetsov components have this form, therefore we get an equivalence of the derived categories of these two associated curves. But then the canonical bundles of these curves, because they're higher genus, ample. So by Bondal-Orlov's reconstruction theorem, so the theorem that I mentioned at the beginning of the talk, this derived Torelli theorem, because the canonical is ample, the derived category determines the curves, so the curves must be isomorphic. But then by this isomorphism of moduli spaces on the previous slide, the isomorphism of curves gives rise to an isomorphism of the varieties or the Fano threefolds x and x prime. Okay. But what about when Kuznetsov components are not necessarily geometric or not known to be geometric? So as an example for this, I'll use the cubic threefold. So this is another one of the 17 deformation families of smooth Fano threefolds. Okay. So yeah, this one's also Picard rank 1. It has index 2 again. And well, of course it's degree 3 because it's cubic. And similarly to the previous degree 4 case, well, we also have the semi-orthogonal decomposition. So again, this O and O1 on the right-hand side, and then the orthogonal to them defined as the Kuznetsov component. But and yeah, as I've written here, a nice description of the Kuznetsov component, as in the previous example, is not known. But we do still have a categorical Torelli theorem. So this one I think was proved in 2009. And it's due to Benadara, Macri, Marotra, and Stellari. So if x and x prime are cubic threefolds, then an equivalence of their Kuznetsov components gives an isomorphism of the cubic threefolds. So same statement as the degree 4 case on the previous slide, but a completely different proof as we're about to see. So I mean the way that this was originally proved, I mean as of now there are more proofs which we'll see a bit later on in the talk. But the way that this was originally proved was using Bridgeland moduli spaces. So if I want to kind of do a concrete proof using Bridgeland moduli spaces, then I always have to fix some kind of numerical thing that the things in my moduli space will share. So for example, if I'm doing slope stability of vector bundles, I have to fix the rank and degree, right? In other words, the slope to consider a moduli space. If I'm doing Giesecke stability, well, I mean, I guess in Giesecke stability, I can also fix the Chern character, and then all of the sheaves in the moduli space will have the same Chern character. So I mean, in this case, in this Bridgeland moduli space case, I should also fix a Chern character, or equivalently a class in the numerical Grothendieck group of the category. But yeah, in this case, let me specifically fix the churn character of the ideal sheaf of a line in X. And I'll call this mathbf v. Okay, and then the other thing I need to fix if I'm considering moduli of stable vector bundles, sheaves, objects, is some kind of a stability condition. So in the case of moduli of stable vector bundles on curves, it's Mumford slope stability. In the case of Giesecke stability, then it's this Giesecke stability condition in terms of Euler characteristics of sheaves. And if I'm doing Bridgeland stability, so stability of objects in triangulated categories, then it has to be a Bridgeland stability condition, sigma. So I'm not going to, I guess, go into details of the definition, but let me just say that, I mean, originally in their proof, Banadara, Macri, Merotra, Stellari, they kind of used an ad hoc construction of stability conditions on the Kuznetsov component of a cubic threefold. Now there's a kind of more general construction of stability conditions on Kuznetsov components of Fano threefolds due to Bayer, Lahoz, Macri, and Stellari, which starts with a weak stability condition on the whole derived category, and then they use that weak stability condition on DBX to induce a stability condition on one of the components, in particular the Kuznetsov component. So these days you can just use that to cook up a Bridgeland stability condition on Kuznetsov component of X. But either way, this is something we have to fix. Okay, and once we've got these, we can consider the moduli space of stable objects of class V in Kuznetsov component. So the next step is to show that ideal sheaves of lines are the only sigma stable objects of class V, so that there aren't any others, and you kind of do this by showing there are no walls. So take a destabilizing short exact sequence and then impose the kind of conditions on the slope and the BG inequalities that come with this destabilizing short exact sequence, and then show that there aren't any possibilities for the kind of destabilizing sub-object. And then, of course, also show that ideal sheaves of lines themselves are sigma stable. Okay, and then once that's done, that gives you an isomorphism of the moduli space of Bridgeland stable objects on the Kuznetsov component of class V to something very classical. So the Hilbert scheme of lines on X. That's just because the Hilbert scheme of lines on X, well, its points are ideal sheaves of lines. Okay. And then, I mean, this isomorphism of this Bridgeland moduli space to this classical thing, that means that if we take an equivalence of Kuznetsov components QX and QX prime, well, that induces an isomorphism of the Bridgeland moduli spaces, which means that we get an isomorphism of the Hilbert schemes of lines on X and X prime. So I mean, there are two things I guess to do here. You show that you have a bijection of closed points, and then you show that it's actually a morphism using the universal family, which gives you an isomorphism. Okay, and then since we arrive at this isomorphism between these Hilbert schemes, then we can use classical results to conclude. So really, maybe I should call this the moduli theoretic plus Hodge theoretic approach, because I mean, after this point, there is some Hodge theory that's being used. So um, I mean, to get from this to an isomorphism of the cubic threefolds, take the Albanese variety of the Hilbert scheme of lines on X. This is known to be isomorphic to the intermediate Jacobian of X, which we'll look at in a bit more detail later on. Well, this gives an isomorphism of the intermediate Jacobians of X and X prime as principally polarized abelian varieties. And then by this by the classical Torelli theorem in terms of intermediate Jacobians due to Clemens, Griffiths, and Turin, again, which we'll see later on in the talk. This gives rise to an isomorphism of X and X prime. Okay. So yeah, I mean the key points are to describe the moduli space with respect to some specific Chern character, hope that it's something nice, concrete, and geometric. In this case, it is. And then use that concrete geometric thing to to conclude your isomorphism of threefolds. Okay, what about so that was cubic threefolds. What about other Fano threefolds from this list of 17 deformation families? What about categorical Torelli statements for them? Well, as an example, let's take the following. So let X be a smooth Picard rank 1 Fano threefold, this time with index 1. So its canonical bundle is just minus h as opposed to minus 2h like before. And degree 10. Well, then it looks something like this. The intersection of the Grassmannian GR25, which is Plücker embedded into P9, with a quadric section and then a linear section of the appropriate size to give a threefold. I mean, a Fano threefold with these numerical with this index and this degree and this Picard rank, this necessarily looks like this, and vice versa. Any threefold which looks like this is necessarily a smooth Picard rank 1 Fano threefold with index 1 and degree 10. And we call this an ordinary Gushel-Mackay threefold. So actually, in this deformation family of Fano threefolds, there's another type of Fano threefold, which is not isomorphic to ordinary Gushel-Mackay threefolds. It's called special. And that's to do with the fact that really what we're doing is we're taking a cone over the Grassmannian and then we're intersecting it with quadric and linear sections. And this ordinary one, these intersections somehow miss the cone point, but for the special one, the cone point is hit, and then this gives you something non-isomorphic to the ordinary Gushel-Mackay threefold. Okay, so that's the geometry of my example. What do the derived categories look like for these Fano threefolds? Well, they have the following SODs. So this time, rather than taking the so remember before we had the exceptional collection O and OXH on the right hand side. This time we can't do that because the index is 1 So this Kodaira vanishing thing won't give us no HOMs from OX1 to OX anymore. So we can't take that as an exceptional collection. What we can take is this vector bundle curly E, comma O. So this vector bundle E, what is it? Well, it's the vector bundle giving the embedding of X into the Grassmannian, into the ambient Grassmannian GR25. And in particular, E is the pullback of the tautological bundle on the Grassmannian GR25. And then I think Gushel showed some nice properties of this vector bundle that it indeed has vanishing um, cohomology from O to E 0. So we indeed get an exceptional collection. And then again, as usual, we define the orthogonal to this exceptional collection as the Kuznetsov component of X. Okay. So again, we're always keeping in mind, does categorical Torelli hold in this case? So does an equivalence of Kuznetsov components of two ordinary Gershon-Mackay threefolds imply their isomorphism? Uh, yeah, so let me say a bit about this. Well, we can do two types of birational surgeries on ordinary Gershon-Mackay threefolds. So I won't go into detail. Just one of them involves a conic, and it's called a conic transform of X. So if you're interested, this is written down in originally in Debar, Iliev, and Manivel's paper on the period map for these ordinary Gershon-Mackay threefolds. Right. So yeah, one of them is this conic transform, and then the other type is this line transform. So another birational surgery involving a line. So XC and XL, they're not isomorphic. But Kuznetsov and Perry, they showed that actually the Kuznetsov components uh, of these two birational surgeries, they agree. So in particular, that means that a categorical Torelli theorem in this case doesn't hold on the nose. So, there's two non-isomorphic things which share the same Kuznetsov component. Okay, but let me remind you, and I guess there's a spoiler here in the key point sentence, but let me remind you again of the SOD. So the SOD is QX, E, and OX. So even though QX by itself doesn't determine X up to isomorphism, if we wanted to determine X up to isomorphism, there's still kind of hope of taking maybe something in between. So not the whole of DBX, but not just QX by itself. And then we're kind of led to guess that, okay, maybe QX and this vector bundle E controlling the embedding of X into the Grassmannian, maybe that's enough to determine X up to isomorphism. So that's kind of the key point I've written here, that this two-term subcategory should determine X up to isomorphism. How do we actually formalize this, and how do we actually package this into a statement just about the Kuznetsov component of X? Because as you can see at the top of the slide, again, this will be a moduli theoretic proof. So the idea is to project this object E into the Kuznetsov component. I mean, let me explain some of the notation here. So my I is the embedding or the inclusion of QX into this two-term subcategory here. And then I upper shriek, that's one of the adjoints to this inclusion functor, in particular the right adjoint. And that's the adjoint we have to take because the left adjoint applied to E would be 0. So there's somehow a canonical choice of adjoint when you're doing this projection procedure. Right, so considering QX and E, this two-term SOD is equivalent to considering QX and this so-called gluing object inside it. So that's what we'll do, and hopefully that's enough to determine X. Right. So how do we go about formally proving this? Well, again, as usual, we should start with some moduli space of stable objects in the Kuznetsov component. So before you'll recall that the numerical class I took was ideal sheaf of a line. And I guess the idea is that you always choose the numerical class with the hope that you'll get something associated to that numerical class inside your moduli space. So I guess in the cubic threefold case, they knew they wanted to recover, or they were hoping to recover this Hilbert scheme of lines from this Bridgeland moduli space. That's why they chose this ideal sheaf of a line class. Well, in this case, we're hoping to actually recover X itself inside this Bridgeland moduli space. That's why I'm choosing churn character of ideal sheaf, sorry, churn character of the projection of a skyscraper sheaf on X. So O little x is just the skyscraper sheaf on X, and then I upper star, it's the projection functor into QX. So again, it's this inclusion, but this time the left adjoint. And another thing I'd like to point out is that, I mean, considering the projection of the skyscraper sheaf and the projection of the ideal sheaf of a point is essentially the same thing. Right. So when we consider this, so now let's switch to working with the projection of the ideal sheaf of a point. When we consider this projection of the ideal sheaf of a point, this is the triangle we get that defines it. I mean, this I upper star, what this really is a left mutation functor along E. Left mutations are defined by triangles in the derived category. And this is the triangle for this left mutation of E applied to IX. There'd be HOMs on this left-hand side, but they've been kind of computed, and this is why we get this direct sum of 3 E's. And then this IX in the middle is just from the definition of this left mutation. Okay, so this is, to summarize, the triangle defining this I upper star IX. Here's another fact that considering HOMs from I upper star IX to E is the same as considering HOMs from I upper star IX to I upper shriek E. So in particular, this is this gluing object that I mentioned above. And this isomorphism between these Hom spaces, this is just because I upper shriek is the right adjoint to the inclusion. Okay, so here's the key point. Consider the following locus of objects in this moduli space. So the locus of objects F in the moduli space such that the x1 from F to this gluing object is 3. So the point is that I upper star IX, this lies in this Brill-Noether locus. You can show that the x1s from I upper star IX to I upper shriek E are 3. So that gives you an embedding of X inside Bn, inside this Brill-Noether locus. That's just because these I upper star IXs, these parameterize the variety X. That's because considering IX is essentially the same as considering Hilbert scheme of points on X, but Hilbert scheme of points on X is just X. And then the next step is to show that okay, you have this X inside this Brill-Noether locus. Well, the next step is to show that this X is the whole Brill-Noether locus. So how do you do that? Well, you assume that it's not. So you assume that Bn is bigger than X. Then you take some object in the complement. Then you show that this object is a vector bundle, that it's stable, and then you use the stability and the fact that it's a vector bundle to conclude that it must be actually the cone of E direct sum 3 to Ix. So in other words, it must be I upper star Ix all along, and thus the complement is empty. Okay. So all of this, I mean, the key point being that we have this isomorphism between X and Bn. This gives the following corollary. So this is joint work with Jiu Liu and Shizhuo Zhang. So if we start with an equivalence of Kuznetsov components, and we specify that this gluing object is preserved. So in other words, phi sends the gluing object of QX to the gluing object of QX prime. Well, then we get an isomorphism of these Brill-Noether loci. So again, you show that it's you show that you have a bijection of closed points, and then you use the universal family to conclude that it must actually be a morphism, therefore an isomorphism. And then because of this isomorphism from Bn to X, we conclude that X and X prime are isomorphic. Okay.
So can I ask a question here to make
Yeah,
sure? So
yeah, of course.
the assumption here is equivalent to having an equivalence between the complement of the structure sheet.
Yeah.
Okay.
Yeah, that's right. Yeah.
And
Yeah,
now,
Oh,
sorry.
sorry, go ahead.
Yeah, no, just curiosity about the notation. So is there any reason why we don't call, why is Kuznetsov component not just the complement of OX?
Yeah, there's a that's a good question. I guess maybe my next slide will maybe answer your question. Yeah, that's a good question. I guess because like defining something as the Kuznetsov component, I suppose the priority isn't like whether a categorical Torelli theorem holds. I suppose maybe usually they're defined as kind of find the biggest kind of exceptional collection possible in your derived category, and then the orthogonal to that like um largest or longest exceptional collection will be your kind of Kuznetsov component. Um, yeah, so I mean, in that sense, maybe that's why it's called the Kuznetsov component. Because I think or like already a while before we did this uh, you know this SOD was written down. So yeah, somehow this smallest residual component is the natural thing to call the Kuznetsov component.
So in this case, we know that Kuznetsov here is indecomposable.
That's also a very good question. I don't think it's actually known for sure. I mean, I'd assume that it is, but I don't think it's actually known. And I don't think it's known for cubic threefolds either, for like a lot of the I mean, if someone knows, correct me if I'm wrong, but yeah, as far as I know, it's not actually been proved. So that's an interesting question, at least for me. Yeah, thanks. And actually, oh, sorry, go ahead.
No, no, just thank you, thanks.
Okay, cool. And I guess I have another kind of answer to your question, Pedro. Uh, I mean, because Kuznetsov components, I mean, by now we can kind of see them as analogs to the category theoretic analogs to intermediate Jacobians. So very often they kind of determine each other. Um, and yeah, I mean, somehow in this case, this complement to E and O, that's the thing corresponding to the Hodge theoretic intermediate Jacobian. So that's, I guess, another reason, like for consistency, why you'd want to call this the Kuznetsov component. But yeah, thanks for the questions.
Thanks.
Okay, so as we just saw, the Kuznetsov component, you need a bit more to determine this X up to isomorphism. But actually, you could ask, what if we just took an equivalence of Kuznetsov components? Can we infer anything from that? Um, and actually, well, I should go to the previous slide. So on this previous slide, we saw this theorem of Kuznetsov-Perry that this QX, Q of conic transform is equivalent to Q of the line transform. I should also say that these conic transforms and line transforms, well, I guess because they're birational surgeries of X, they're birational. So this kind of hints at the following question, does an equivalence of Kuznetsov components imply birational equivalence of the varieties in this case? And this is actually a conjecture that Kuznetsov-Perry made in a subsequent paper, I think. And they made it for Gushel-Mackay varieties of any dimension, actually. Um, so, I mean, this theorem, this one's due to myself, Shunlin, Jiu Liu, and Shizhuo Zhang. Um, uh, I mean, this theorem proves this conjecture in this dimension three case, and yeah, for ordinary Gershon-Mackay's. Um, Right, so how does the proof go? Well, I just want to mention the proof because it's again it's moduli theoretic. By the way, do I have 1 hour or is it 1 hour
Uh,
30?
you can go 1 hour 30. Yeah.
Okay. I don't think I'll use the whole 1 hour
Okay,
30, but yeah, okay, thanks.
that's fine.
Um, okay, cool. So I just want to say a few words about this proof because it is moduli theoretic. Um, so as usual, let's fix a numerical class. This time the numerical class is a bit more mysterious. I suppose it's not something like the skyscraper sheaf of a point or ideal sheaf of a line. It's the class of this gluing object. And I've said it's a -1 class. This just means that with respect to the Euler form, it squares to -1. Um, there are two possible -1 classes in the numerical Grothendieck group of the Kuznetsov component in this case. Uh, and why is that relevant? Well, it's because equivalences, I mean, we can't guarantee that, X will be taken to the analogous X prime on the numerical level by an equivalence, but we can guarantee that a -1 class gets taken to a -1 class. On the numerical level. So somehow we only have two moduli spaces to consider. And that's exactly what we do. So for this first -1 class, we show that this moduli space is is equivalent to something, again, very geometric. So the CMX is the minimal surface of the Hilbert scheme of conics on X. So what do I mean by that? Well, the usual Hilbert scheme of conics on X, it has a rational curve on it. So contract this, and then you get the minimal surface, and that's exactly what this Bridgeland moduli space is. And then for the other -1 class, we show that it's isomorphic to this Giesecke moduli space of sheaves on X. So with rank two, first Chern class 1, and then second Chern class 5. And actually, this thing's isomorphic to the minimal surface of the Hilbert scheme of conics on the line transform of X. So a bit of a mouthful, but that second isomorphism is actually useful for the later bullet points. But the key point is these two Bridgeland moduli spaces with respect to these two -1 classes, they're nice and geometric. So as I said, an equivalence preserves -1 classes, so this X gets sent to, well, either X prime or Y prime in this numerical K group of QX prime. Well, that means that on the moduli space level, we get isomorphisms between either CMX and CMX prime. So this is if X gets sent to X prime on the numerical class level, or we get this second isomorphism of Hilbert of minimal surfaces of Hilbert schemes. So this is the case where X gets sent to this Y prime numerical class. Okay, so we have these isomorphisms of moduli spaces. And I guess you can see that this is still somehow mirroring the original Bernardara Macri Marotra Stellari proof cubic threefolds. You know, we're investigating some specific moduli spaces, and then we're inducing isomorphisms between the resulting nice Hilbert scheme type things. Okay, so but where do we go next in this case? Well, the equivalence phi that sends this gluing object to some conic on X prime. Yeah, I mean, you can think of this gluing object actually as the projection of the ideal sheaf of a conic on X. So really, I want you to just think of this I upper shriek E as like some distinguished conic on X. The point is that this equivalence phi sends this distinguished conic on X to some kind of random conic on X prime. And the point is, because this I upper shriek E, it's some distinguished conic, when you blow up the minimal surface of the Hilbert scheme of conics on X at this distinguished conic, you get back the actual Hilbert scheme of conics on X. And then when you blow up this minimal surface of the Hilbert scheme of conics on X prime at this random conic C, not distinguished anymore, you get the conic transform that you get the Hilbert scheme of conics on the conic transform of X prime. So somehow the point I want to make here is that blowing up your minimal surface of your Hilbert scheme of conics at a conic gives you the Hilbert scheme of conics on the conic transform of X. It's just that blowing up at this distinguished thing, then you don't do a conic transform. That's the point of blowing up at this distinguished conic. Okay. The upshot is that this blowing up procedure, from these isomorphisms of minimal surfaces, you get these isomorphisms between actual Hilbert schemes of conics. It's just that now they're between, um, for example, the first one is isomorphism of Hilbert scheme of conics on X, and that on the conic transform of X prime. And then this more complicated looking one on the right. And then Logachev, I think from the 80s, has a reconstruction theorem where the Hilbert scheme of conics on a Gushel-Mackay threefold determines X. So that's where we get these isomorphisms X to X prime C, and then this one from. But because these were all birational surgeries all along, we get that in both cases, X is birational to X prime. Okay, and then I think maybe another point just quickly worth making here is that so this gives a birational categorical Torelli theorem. If we look at this bullet point, and if we were to specify that this phi sends this distinguished conic, this I apostrophe E gluing object, to the corresponding distinguished conic on the X prime side. So in other words, the condition from this refined categorical Torelli theorem that I had on the previous slide, then you'd get that X and X prime are actually isomorphic. So this is another way of proving this refined categorical Torelli theorem. If you add the condition that rather than just letting phi send I apostrophe E to some random conic, it sends it to the corresponding gluing object, then you'll get an isomorphism of X and X prime. Okay, so sorry, maybe that was a bit too scatterbrained as a proof, but I hope that at least some parts were clear. Does anyone have any questions? Okay, if not, let me just quickly speed through some the kind of Hodge theoretic side of my talk. So the previous side was all moduli theoretic. Now I want to say a few words about the Hodge theory side of things. So um, yeah, I mentioned the intermediate Jacobian of threefold before, but here it is explicitly defined. So we take the 1-2 part of the Hodge decomposition of X, and then quotient out by the integral third cohomology of X. And this was used by Clemens Griffiths and Turin to prove the classical Torelli theorem for cubic threefolds. So this I mentioned earlier in the talk because this was actually used in the moduli theoretic proof of categorical Torelli for cubic threefolds. Right, so the statement is that JX isomorphic to JX prime is PPAVs. That gives an isomorphism of X and X prime. So Perry and Bernardara Taboada defined the intermediate Jacobian of a subcategory of DBX. They did this by considering the topological K theory of the subcategory and then putting a Hodge structure on it. At least this is what Perry did. I'm not as familiar with Bernardara Taboada's proof or construction, but it boils down to the same thing. So they get this categorical version of the intermediate Jacobian, which I've written as just mathbf J. And the kind of key point is that this categorical construction of the intermediate Jacobian of a category, if you apply it to Kuznetsov component, then it gives you back intermediate Jacobian of X. So this is what I was mentioning earlier about the analogy between QX and JX. This kind of really makes it explicit. And the upshot is that whenever a classical Torelli theorem holds for a Fano threefold, so does a categorical Torelli theorem. Um, so indeed, we can use this corollary to prove some cases of categorical Torelli for Fano threefolds. So for example, for the cubic threefolds case, which we already looked at the moduli theoretic approach for, I mean, here we can just assume an equivalence of Kuznetsov components. I mean, this gives an equivalence of these bold J's of these Kuznetsov components, and then that gives you an isomorphism of the intermediate Jacobians, which by Clemens, Griffiths, and Turin gives you an isomorphism of x and x primes. But the point is that this, this doesn't always happen. Like classical Torelli theorems haven't been proved for all of the deformation classes of Fano threefolds. Right. So for the kind of remaining cases, which can't be, which for which classical Torelli doesn't hold, and for which you can't use moduli theory. And the reason why you can't sometimes use moduli theoretic techniques is just because of Bridgeland stability conditions in certain cases behaving badly. So you need some other kind of approaches. So let me tell you about another Hodge theoretic approach. So this one applies to weighted hypersurfaces. So there's a classical Hodge theoretic construction called the infinitesimal variation of Hodge structures. So it's three pieces of data. It's the infinitesimal deformations of X in its moduli. So this is given by H1 of the tangent bundle of X. Infinitesimal deformations of the intermediate Jacobian in its moduli of PPAVs, principally polarized abelian varieties. So this is what this direct sum is giving, infinitesimal deformations of the intermediate Jacobian. And then the third piece of data is this derivative of the period map. So the map between infinitesimal deformations of X and infinitesimal deformations of the intermediate Jacobian. Why is this the derivative of the period map? Well, it's because the period map, remember, at least in the case of these Fano threefolds, goes from moduli of Fano threefolds of a certain deformation class to moduli of the appropriate PPAVs, and it sends an X to its intermediate Jacobian. Right, so we have this construction of infinitesimal variation of Hodge structures, and the point is that for weighted projective hypersurfaces, so this the setting of this approach, the above data can be expressed very nicely and very simply in terms of graded pieces of the Jacobian ring of X, where the Jacobian ring means this polynomial algebra modulo the ideal generated by the partial derivatives of the function defining the hypersurface. Right. So actually, I just want to say, so yeah, H1 of Tx can be defined as a graded piece. This thing can be defined by a graded pieces, and then there's like this. Then there's multiplication also in the Jacobian ring, or between different graded pieces of the Jacobian ring, and then all of this together allows you to express this, and then the map just in terms of graded pieces of the Jacobian ring. So Lin, Renemo, and Zhang, they define and relate something called the Hodge-Serre algebra of the Kuznetsov component of X. So this is defined as the following direct sum. So HOMs between the Furey-Mukai kernel of the identity functor of uh, the Kuznetsov component, and then the Furey-Mukai kernel of the nth power of the nth shift of the Serre functor of the Kuznetsov component, and then sum over all possible m's and n's. So they relate this thing to the Jacobian ring of X, uh, specifically to certain graded pieces of the Jacobian ring of X. That means that equivalences of Kuznetsov components, because everything's somehow functorial, give rise to isomorphisms of the relevant graded pieces um, of the Jacobian rings of X and X prime. And then classical Torelli type results in terms of the graded pieces of the Jacobian ring recover X. In particular, sometimes classical Torelli theorems don't hold in terms of the intermediate Jacobian of X, but they do hold um, in terms of the Jacobian ring of X, and these are the classical types of results that Lin, Renemo, and Zhang use um, to conclude their categorical Torelli theorems. Okay, and finally, so I know Hannah gave a Hannah Dell gave a talk here I think a few months ago. So I won't spend too much time on this because I think this was the focus of her talk. Um, but I will say just a few words to kind of finish off the talk. Um, so I've written that this approach works for cyclic covers as a subset of weighted projective hypersurfaces. That's because whenever I take a cyclic cover of some weighted projective space, then it's going to be a weighted projective hypersurface. So Lin, Renemo, and Zhang's theorem it covers the cases we do, but I think this is also independently interesting because as you saw in Hannah's talk, this gives a relationship between equivariant Kuznetsov components and the middle primitive cohomology of the ramification in these cyclic cover cases. So the precise statement of the theorem, so this is with Hannah and Franco Rota, who's who's in Orsay in Paris. Um, uh, so let X and X prime be cyclic double covers of weighted projective space ramified in Z and Z prime, their ramification divisors. And suppose we have an equivalence of these mu2 equivariant Kuznetsov components where the mu2 is the involution at the on the double covers. Then we get a Hodge isometry between the middle primitive cohomologies of Z and Z prime. And then for a few of the deformation classes of smooth Fano threefolds, which are cyclic covers, and for which a few other conditions hold, we get as a corollary categorical Torelli theorems for these deformation classes. So here's a summary of because I've been alluding to these 17 deformation classes all talk. So here's finally a summary of everything that's known. So I've kind of omitted a few of these deformation classes have two different types. So for example, in this degree term, there's ordinary and special. I've kind of omitted that for simplicity. Um, but and yeah, sorry, ignore the ignore the reference numbers here. I've just lifted this from an application I'm writing. Um, but in particular, there is still these two open cases. But the list is almost done at this point. So yeah, I think that's where I'll stop. Thanks everyone for thanks everyone for listening. Happy to take any questions.
Yeah, thank you very much for a nice talk. So is there any questions from the audience?
So on the table in the previous slide, for the
Yes, yeah.
first few items, it says NA for the categorical Torelli. So there is no categorical Torelli at all, like not even in the rational sense.
Yeah, so this is a good question. Sorry, I should have said it's NA in the sense that the moduli of these ones are rigid. So for example, for P3, there's only one P3. So yeah, I guess it doesn't make sense. Yeah.
Okay, thanks.
Yeah, you're welcome. Thanks for the question.
And do you think you can pull off like similar tricks for the moduli theoretic approach for any class of varieties with non-trivial SODs?
Yeah, that's a good question. So this bad behavior of the Bridgeland stability conditions is really the sticking point because yeah, actually let me I guess I've got the table here. So for a lot of these low genus cases, for example, some of which are open and some of which are I've written only have Hodge theoretic proofs. For all of these, actually, we have got a moduli theoretic statement from in a paper with Jiu Liu and Shizhuo Zhang, in the sense that the moduli space of the Kuznetsov component with respect to the ideal sheaf of a point, taking that numerical class, that moduli space is actually X itself. So if we could somehow control the stability conditions in those cases, then it would be very easy to conclude an isomorphism between X and X prime. The problem is that some of these cases, I mean, the key thing that the stability conditions need to satisfy is this Serre invariance. So invariance under the Serre functor of the Kuznetsov component, which ensures that you kind of know where the stability condition lands in the stability space of the Kuznetsov component of X prime. The problem is that for some of these cases, if I remember correctly, it's actually known that the stability conditions are not Serre invariant. So yeah, this kind of this is a major problem for the moduli theoretic approach. That's not to say that maybe some workaround can be developed, but it's something it's not immediately obvious to me how you'd do that.
I see, thanks.
You're welcome.
Any more questions?
So are there any similar examples other than Fano three-fourths?
Yeah, that's a good question. So the I guess Fano right, okay, so I mean Fano varieties in general are a good source for this. So it's the cubic fourfolds, for example. There are categorical Torelli statements for cubic fourfolds. So Kuznetsov components of cubic fourfolds being equivalent. That there you need some extra stuff that the equivalence functor commutes with another functor, and then that gives you an isomorphism of the cubic fourfolds. Off the top of my head, I can't remember any other cases, but for there are general type varieties which admit non-trivial SODs, and in particular some of these SODs admit phantom subcategories. So phantom subcategories, meaning that the Hochschild homology vanishes I should say quasi-phantom because the Grothendieck groups they don't vanish, but they're torsion in at least the cases that I know. But it's an interesting question to ask there whether this phantom subcategory determines X, but as of yet that's not been proved. But yeah, lots of these questions that you can ask.
Maybe a similar question, maybe the answer is obvious, but so what for Del Peso surfaces, why I haven't heard people talking about this for Del Peso surfaces, is there a reason?
So Del Peso surfaces, I guess their SOD, so their SOD is DBP2 and then like all of the exceptional, the exceptional objects corresponding to the exceptional divisors. So I guess the first question there is like what should we take as the Kuznetsov component, and I feel somehow you'd need the whole subcategory. Oh, sorry, the whole DBX there because I guess DBP2 that's not enough. Somehow you need the data of all of the exceptional divisors, I feel. So I think that's probably yeah. Even for I guess some of the Del Pezzo surfaces they're rigid and they're moduli. So for a lot of them it would be this like kind of NA reason that I've written here. But for the ones that aren't rigid and they're moduli, I guess still I feel you'd need all of the.
And maybe another question. So do you know if there's relative versions of this for vibrations with relative dimension 1, 2, 3?
No, I don't know. That's a good question. I feel, yeah, probably if you wanted to do, there is this construction of stability conditions in, at least if you wanted to take a modular theoretic approach to this, there's the construction of stability conditions in families due to due to lots of people. I won't try to name all seven. But yeah, perhaps one could use that technology there. But yeah, that's a good question. I don't know. No.
Any more question?
Maybe one more question about the moduli theoretic approach.
Sure.
So for all the cases you have worked on, you basically try to realize the moduli of the Kuznetsov components as some geometric objects, but how do you decide which one?
Yeah, that's a good question. So I mean I guess for these cubic threefolds where the thing ended up being the Hilbert scheme of lines, I mean I suppose there the idea was that they already knew that if you apply the Albanese to the Hilbert scheme of lines, you'll get intermediate Jacobian back. So somehow they wanted to recover Hilbert scheme of lines, so that's why they chose this ideal sheaf of a line. I mean, we knew that there was this Logachev's reconstruction theorem, and somehow generally there's like this thing where on the index 2 side it's lines, and then on the index 1 side it's conics. So somehow we knew we needed to work with Hilbert schemes of conics somewhere down the line if we were to use these classical results later on to recover the isomorphisms. Yeah, and then we computed the projection of this or rather this gluing object, and then we saw that this thing's actually very related to conics on X, And yeah, I mean, then somehow in that case we were lucky that this gluing object is so. Well, I mean, lucky. It depends how you think about it, but in that case, the gluing object is related to conics, and yeah, then everything kind of falls into place.
Okay, thank you.
Yeah, you're welcome. Thanks.
Any more questions? No? Then yeah, let's thank the speaker again. Thank you very much. Thanks.
Thanks for having me.